All right. So now we talked about solution concentration and how to calculate it. Now let's talk about what it actually looks like in a solution if you were to like shrink down and kind of see around what a solution looks like. Ionic compounds form what are called electrolyte solutions. So these are electrolytes are what happens when we dissolve ionic compounds. And essentially what happens is, right, so here is, for example, your salt. So for example, something like sodium chloride is an ionic compound. So, you take a crystal of salt and you throw it in water. At first, it starts out as this big network, this big ionic solid. We talked about those. But what's going to happen when it's in water is it's actually going to be broken up into its two different constituent ions. So in solution, instead of being sodium and chloride stuck together in this large network solid, it actually will break apart into its sodium ions and its chloride ions. Okay, so just to kind of color here. So here I have my orange or my green sodium ion, my green chloride ions. Your chloride ions are now separated from your sodium ions. There's no longer a covalent bond, and they're both surrounded by water. Okay, so water has this polar end, is a polar compound. Let's actually just draw it out here. The back end with the oxygen has a partial negative charge, and the front end with the hydrogen has a partial positive charge. Okay, so these partial positive charged ends will end up aligning with that negatively charged chloride ion. And then the opposite happens for the sodium ion. So now my sodium ion I have is now dissociated and floating around separate from that chloride ion. And water is again sort of aligned, but this time the oxygen butt is aligned to help solvate that proton, that positively charged ion, right? So bottom line is when you take an ionic compound and you dissolve it into water, it actually breaks apart into its two different components. In this particular example, the sodium ions are floating around independently of the chloride ions. That would be an electrolyte solution. So these are ionic compounds. Non-electrolyte substances are ones that are formed from covalent compounds. And a covalent compound would not break up into different constituent atoms. Okay, so an example would be to talk about how we talked about carbonated water that has CO2. Carbon dioxide is then dissolved in that water, but it's not like the carbons and the oxygens are floating around independently. You still have molecules of CO2 covalently bound, and those molecules are just floating around independently. This would be called a non-electrolyte solution. So again, these are made from covalent compounds, whereas electrolytes are made from ionic compounds. And this name comes from the fact that electrolyte solutions, again, those made from dissolving ionic compounds, they conduct electricity, whereas non-electrolyte solutions, again, those made from dissolving a covalent compound, those do not conduct electricity. Okay. So for example, here is this light bulb, and this light bulb is going to turn on if the solution conducts electricity. So with water all by itself, it does not. That's what's pictured here. Water all by itself, it will not conduct electricity. If you dissolve a salt in there, this will become an electrolyte solution. And that does conduct electricity, so that's why that light bulb's turned on. So this would be something, for example, sodium chloride. But if you take and again, the key being that it's ionic, but then if you take a molecular or a covalent compound, so for this one, this example is glucose, which is C6H12O2. Sugar, glucose, is very soluble in water, But when you dissolve it, you don't break apart those sugar molecules. They stay all covalently bound. This is a covalent compound. And again, that does not conduct electricity, so it is a non-electrolyte solution. All right, and then the ratio of ions will dictate their concentration in solution. So what do I mean by that? So barium nitrate is BaNO3 2, right? And I know that by looking at the charges of the barium and the nitrate. That's how I determined I needed 2 nitrates per barium, okay? So when I dissolve this in solution, note that the nitrate is pictured in red. I have twice as many nitrate ions floating around as I do my barium ions, which are pictured in gray. All right. Likewise, aluminum chloride. This would be AlCl3. So I have 3 times as many green chloride ions floating around as I do my gray aluminum ion. And likewise, sodium phosphate is Na3PO4. So I have 3 times as many blue sodium ions floating around as I do my yellow phosphate ions. Okay. So quantitatively, if we're going to calculate the concentration of each ion in these solutions, we can do that. We're going to have to keep in mind that those subscripts, okay? So what we would call the mole ratio. So let's just do the first example here. We have lithium chloride. So 1.050 moles per liter of lithium chloride. 1.150 moles in 1 liter, and this is of lithium chloride, okay? If I want to know the concentration of each ion, oh, it says of chloride ions, sorry. So I'm going to figure out the concentration of chloride ions. I'm going to need to include the mole ratio where 1 mole of lithium chloride contains 1 mole of chloride ions. Right? And I can tell that because when I look at the formula lithium chloride, there's no subscript here. Oh. All right, so punch this into my calculator. I get 0.15. That's what my calculator would spit out. I'm going to pay attention to units. And moles of lithium chloride cancel out, but I'm left still with moles of chloride. So this would be moles of Cl minus over liters. Those are my units. And then if I'm going to do sig figs, I'm going to note that I should have 3 sig figs. So I should actually throw a 0 on there as well. So this is 1.150 and then molar chloride, right? So moles per liter is again just that big M. All right, the next one we have 0.150 moles of magnesium chloride. Oops. Divided by 1 liter. And here I'm going to use the mole ratio where 1 mole of magnesium chloride contains 2 moles of chloride ions, right? Because if I take my magnesium chloride, I have this 2 here, which represents that per mole of magnesium chloride, I actually have 2 moles of chloride ions. So now punch this into my calculator and I get 0.3. Again, paying attention to units, moles of magnesium chloride cancel. So I'm left with moles of chloride over liters. And then I'm going to note that I should have 3 sig figs. So this is 0.300 molar chloride ions. Whoops, Cl minus. Okay. I'm going to leave that third example to y'all. And how do we go about preparing a solution from a solid? So this uses what's called, you can actually do it in a bunch of different types of glassware, but the most accurate way to do it is to use what's called a volumetric flask. That's this guy here. Volumetric flasks are really, really good at measuring just one volume. So this particular volumetric flask would measure 500 milliliters, but it would do it with 5 sig figs, which is a lot. And what you would do is you would fill it up such that you stopped at this little etch that's on the neck of that glassware. And once your solution has reached that mark, that's how you know that you're done. Okay. So what you would do is you would first have to calculate how much solid you would want to in your solution. So if you wanted to make a 3 molar solution, you would have to do the calculation to figure out how many grams of solute that would require. And you would go to your balance and you would measure that out. So that's this first step here. Measure it out, however much solid you were supposed to put in there. Then you add the solid to the volumetric flask. And then you fill up the volumetric flask with whatever your solvent is. In this case, it says ethanol. 99% of the time, it's actually water that we're using as our solvent. But whatever your solvent is, you're going to start filling your volumetric flask up. After you get about halfway there, you're going to stop and you're going to just swirl your flask until all the solute is dissolved. It's really hard to dissolve the solute once that flask is completely full. So you actually stop about halfway, start swirling it around until everything's dissolved. Once it's all dissolved, then you fill it up all the way to that little tick mark that's on the glassware. Okay, but that's how we would go about preparing a solution. Actually, at that point, usually it's capped and inverted a few times to mix it up so that it's all perfectly homogeneously mixed. Okay. So now we're going to do a few calculations here back to back. So this is from an aqueous solution of glucose. Determine one, the molarity that you would get if you had 2 liters and that contained 50 grams of glucose. The volume of this solution that you would use that would contain 250 moles of glucose. And then finally, the number of moles in 0.5 liters of this solution. Okay, so this first one is actually one, and I'll again tell you the molar mass of glucose is that 180. What is it? 180.15588 grams per mole. Again, I got this by using the periodic table and looking for carbon, hydrogen, and oxygen and accounting for the fact that it's C6H12O6. That's how I got that number. Okay, so 50 grams of glucose. If I want to determine the molarity of this solution, I have to first convert that to moles using the molar mass. So 50.0 grams times 180.15588 grams in 1 mole. Punch that into my calculator and I get 0.138. No, I don't. I lied. I'm sorry. I'm looking at the wrong thing. I get 2.77537. Looking at my units, I'm left with moles. So now I'm in moles glucose. And I'm going to note that I should have 3 sig figs in this number, but I'm not going to round yet. I'm going to then take this and divide by my 2.00 liters. And so my solution concentration will be 0.138768 moles per liter, or molarity. And I should have 3 sig figs. So I'm going to take 0.139 molar. That's going to be my final answer for part A. Now I want to see, now the next for part B, so this was A. For part B, it's how many liters of this solution is required to get to 0.250 moles. So I'm going to take 0.250 moles And I'm going to multiply it by the inverse of my concentration, because this is moles per liter. The big M is moles per liter, and I want moles on the bottom. But note, I am going to make sure to use the unrounded answer, right? Because the rounding is only ever done in the very last step of a calculation. So I'm going to use my unrounded answer that just has the number of sig figs marked. That would be the most accurate way to do these calculations. And I get 1.80155. Looking at units, moles will cancel and I'm left with liters. And I should have 3 sig figs. So 1.80 liters. That's my final answer there. Okay, so make sure you're taking those unrounded concentrations to use in future calculations. And then lastly, what are the number of moles of glucose in 5 liters of solution? Now I'm going to use my same concentration here. Again, I'm actually going to use the unrounded form, and I'm going to put it in that conversion factor of moles per liter. Since I'm going to start off with 0.500 liters on top, I'm going to put the liters on the bottom. Again, using that unrounded value that has my sig fig marked, punch that into my calculator, and I get 0.0693. 384. Looking at units now, liters cancel out and I'm left with moles. So this is how many moles of glucose there are in 0.5 liters of solution. And I should have 3 sig figs, so 0.0694 moles of glucose. That's my final answer. Okay, so first we calculated the concentration in molarity, and then we used that molarity as a conversion factor to either go from moles to liters or from liters to moles. We could go either direction.